Hello and welcome to the lecture on augmented reality. Today's topic is camera calibration. First of all, why should you care about camera calibration? Well, for augmented reality to function properly, one needs to take into account the camera properties. If one does not do this, things do not align properly. So take a look at the following picture. Here we try to overlay the red car, which is in the real world, with some green mesh in the virtual world. And as you can see, this does not work properly because we did not take into account the camera properties, notably the distortion of the lens. This means that the pose is estimated correctly, so the location of the car is right, but because the distortion is not taken into account, we have like gaps like in this area of the image. If one knows, however, the distortion parameters of the lens, one can undistort the image and then things align properly. This is what you see in the following image. As you can see, the gap here is now gone and things properly align, and now we can start highlighting tires or doors or place whatever annotation one do in augmented reality. However, due to the undistortion, we now got these black regions at the edges of the image. These are regions that are not visible in the original image, precisely due to the distortion. So one more thing that one typically does is to increase the zoom level of the virtual camera so it focuses on the valid region of interest of the image. This is what you see in the following slide. So we slightly zoomed in, so the black image borders are gone. And this is typically what happens in the background with any augmented reality application where there's a live video stream. The incoming images are undistorted such that our naive rendering aligns well with the background camera images. But even though the focus of this lecture is augmented reality, there are also other applications where knowing the lens distortion or generally the camera parameters is beneficial, which we will take a look at in the following. So the first application which naturally comes to your mind is probably photography, because sometimes you do not want to have this distortion in your photos and you want to remove it so that your pictures look better. So this is one application. Many camera vendors nowadays do this actually in the camera. So you take so they can build cheaper lenses and then remove the distortion in post-processing on the camera. Then there are many or most vision algorithms require linear data, and the lens distortion is inherently nonlinear, and this prevents many things to be computed. So some examples of algorithms that require linear data is multi-view stereo. So you have like several photos of the same object and then you want to reconstruct the geometry. This requires a linear coordinate system, and therefore we have to remove any non-linearities. Similarly, stitching, where you have again multiple images, but you want to combine them to a single panoramic view. And for this, you also want to remove the non-linearities to be able to do that. And finally, we have the augmented reality application, which basically boils down to the perspective endpoint problem. You can find a reference to a rather recent paper on this problem. And what is this perspective endpoint problem about? Basically, you have some 3D points where you know their exact 3D coordinates, and this is what is depicted on the left. So we have like one image of this T package, and we know the pose in the image, which is denoted by the green wireframe. Therefore, we know each point on the surface of the package. Then we are presented with a new image of the same object, but this time we don't know the green outline. However, we can match some of the points some of the 2D points in the image to the reference points up here. This is like just this image. So the problem is deriving the new wireframe position just from these matches. So we have on one hand the 2D points, and then we have the known 3D points. And the n in here describes how many of the matches we have. So given this data, we then compute the new position of the wireframe. And this is like the foundation of all of augmented reality applications nowadays. So now that we know that we should care about camera calibration, let's turn to the outline of this presentation. First, we are going to lay out some of the mathematical foundations we need to calibrate our camera. So to say, we start with mathematically modeling our camera. Then we will add a lens to this mathematical model, discussing some of the lens distortions we are considering, and only then we turn to the calibration. Here we will first discuss the targets, which we will introduce a probability then, and finally we turn to the calibration poses. Again, it will be discussed when we arrive there. So what is the mathematical model for the camera we use? Basically it is this. What you see is a sketch of the pinhole camera model. As you probably can recognize, this sketch is rather old because the pinhole geometry is used since at least the 17th century, and it was first introduced as a drawing aid. So some guy was sitting in this black chamber and drawing on the back wall, and this helped him capturing the real world outside. And this is exactly what we want to do as well. This model is rather simple. It only consists of this black chamber, which has a hole on it outside at one side, and then rays of light from the outside travel through this hole and are projected on the back facing wall of the chamber. So what we want to do is to capture the travel of light, which is sketched out here mathematically or more formally on the next slide. For this we define a function p, which is like shorthand for projection, which takes a 3D point big P and maps it to a 2D point small p. So this is the world point outside, and this is a point on the back facing wall of the dark chamber. Here again, which components this points consist of. So this is a 3D point, this is 2D point. And then the function also has some other parameters like R, T, and C. And these are typically the ones we want to derive during calibration. Notably, C are the calibration parameters, and R and T are the position of the camera in the world. R is for rotation and T is for translation. And together these two parameters are called the extrinsic parameters because they are like outside of the camera. It's like the position of the camera in the world, so it's not inside the black chamber. Yeah, here it goes again. We have T, the translation, and R, the rotation. And typically the direction this is describing is world to camera. So against intuition, the camera is always at the origin and the world moves around the camera. So this is easier to, it will be easier later on. One thing to note here is the rotation. It says it's a 3D rotation, but typically we describe the rotation by a 3x3 matrix. And now you can wonder how does this fit, because the 3x3 matrix has 9 entries and thus 9 degrees of freedom, but our rotation only has 3 degrees of freedom. This means that the matrix needs to be restricted such that although it has 9 entries, they are only 3 degrees of freedom. So to this end, the matrix, or first we require the matrix to be orthogonal. This means that the inverse of the matrix is simply its transpose. So yeah, this is what this says. And a consequence of these is that we now only have the upper triangular part of the matrix, which is free, because the lower triangular matrix is coupled by this relation. This relation is equally to the determinant squared of the matrix being 1. However, this is still not enough to arrive at only 3 degrees of freedom, because the upper triangular matrix still has 4 entries. And the way we further restrict this is by requiring the matrix to be special. Special means that the determinant is strictly +1 and not -1, which is still allowed here. And together these two requirements form a group which is called special orthogonal group. And because we are talking about 3x3 matrices, it's special orthogonal group of 3. And yeah, now we arrived at a 3x3 matrix which only has 3 degrees of freedom. A particularly useful test is to always check this if you encounter a rotation matrix, that its determinant is +1. If it's not, it is not a rotation matrix. It might involve some mirroring and shearing and things you do not expect. So if working with linear geometry something goes wrong, always check that you actually have a rotation matrix. Furthermore, there's another way to express a rotation besides the matrix. It is the Rodriguez vector, which conveniently only consists of 3 entries, and therefore it's a Rodriguez vector. You don't need any more checks, and it's the most compact representation of a rotation. There's also quaternions, but we skip them here. We mentioned the Rodriguez vector here because it's like the typical rotation representation in the OpenCV library. And you can always convert a Rodriguez vector back to a 3x3 matrix, or you can go also from a 3x3 matrix to the Rodriguez representation. And yeah, you can use the Rodriguez vector where you have lots of rotations, because it's like only 1/3 of storage compared to the matrix. Also, if you want to have the derivative of a rotation, use the Rodriguez vector, because with the matrix it's not straightforward, but here it is. Okay, now that we know what rotation and what a translation is, let's take a look how to actually apply such transformation. This means we have given a point in world coordinate space, and we want to transform it back to the camera coordinate space. Again, remember that the camera is assumed to be at origin. This is done as following. First we apply the rotation to the point, and then we apply the translation. However, this is slightly cumbersome, because you always have to remember whether you first add the translation vector or you first do the rotation. Like, it's pretty clear, because dot has a higher precedence than plus, but nevertheless, there's slightly simpler or more straightforward representation of the transform, namely homogeneous coordinates. For this, we extend our world point by the homogeneous coordinate w, and we set it to 1. And now we can express the whole transform as a single matrix vector multiplication. For this, we build a matrix of dimensionality 4x4, and the upper left corner is the 3x3 rotation, and then we add the translation to the right. And for the bottom row, we have 3 zeros and then the coordinate 1. And if you use this matrix, it exactly does the same like the above. It first applies the rotation and then the translation. Okay, so now that we know how to go from world to camera, let's talk about the reverse direction. Now we have a 3D point in camera coordinate space, and we want to get the according coordinates in world coordinate space. So this means we need to go the reverse direction. If you recall, we first applied rotation and then translation, and so we have to do this here accordingly. We first invert the rotation, like here. Recall that the inverse of a rotation is just a transpose of it, and after we inverted the rotation, we can remove the translation. This is now slightly more complicated formula, and when we are using homogeneous coordinates, like here, it is slightly more convenient. Of the inverted matrix, it already like did this thing and rotated the translation direction. However, take in mind that, or keep in mind that the inversion is a much more involved operation than this one, and if you are like in a performance sensitive area, you should always do this because it's faster than doing a 4x4 inversion. Okay, now that we have covered the extrinsic parameters, let's turn to the intrinsic parameters of the camera. For this, let's take a look at this pinhole representation again, and this time we have a 2D schematic view of everything. The first thing to note about this sketch is that we flipped the back wall from here to the front because it makes discussion slightly easier. And now we want to derive the mathematical equation of the ray. The ray is this red line in here, and it connects any 3D world point in camera coordinate space, like here, to the origin of the camera coordinate system. And while traveling along this ray, at some point we intersect with the image plane, like here. This is exactly the same, like if the image plane would be behind the camera origin, then it would be intersecting somewhere here. So in this image we have some additional geometrical properties, namely we have the width and the height of the image plane. These are typically measured in pixels. And if we intersect the ray with the image plane, we get an intersection point UV, and it's typically also in pixel coordinates. Then we also have this thing here called principal point, but we will discuss it only on the next slide because then it's slightly more obvious what it does. Okay, so I'll turn to the next slide. Here, this is again the same geometry like in the previous image, but we are looking on it from the side. So this simplifies the discussion a little bit because we only have a two-dimensional space here, and hence the x component of the world point is dropped. So what we want to derive here is given some world coordinates y, z, the image coordinates small y, f. And what we are going to use here is the intercept theorem, which basically relates this vector in blue here and the distance to origin with this small vector in blue with this distance. And this distance is z, the distance of the point to the camera origin. And this distance is f, and it's the distance of the image plane from the camera origin. Note that we again use the same schematic like initially with this old sketch, where the image plane is behind the camera origin. Okay, so the relation is y derived by z is small y derived by f, and we are interested in small y, so we modify the equation like this. And yeah, basically we could be done here, but we also add this principal point cy. So why do we do this? Because the image plane, which is like this dashed gray line here, does not have to be aligned with the optical axis like this one. And it's also not done in this example, where the center of the image plane is here. And therefore we have like this offset cy between the optical axis and the center of the image plane. And to compensate for this, this is why we add the principal point or the cy offset here to move the coordinate to the image coordinate system. So this point is still in camera space, and when we add the principal point, we are now in image space, like in pixels finally. Yeah, and this discussion allows to assemble our final camera model, which we do on the next slide. So this is the final camera equation, and as we typically do with matrix notation, we read it from right to left, and here we have the 3D world point P, then we have the rotation and translation. The brackets indicate that we somehow applied to the P, like you can think about the 4x4 matrix here. And now we have our intrinsic matrix K. This basically encodes the intercept theorem from the last slide. Notably, we pulled out the Z division beforehand. This means that the points which you multiply with this matrix already are divided by Z, and the components are X by Z, Y by Z, and then Z by Z, which is 1. And what this means, if you take at the X component here, that we multiply Fx by X divided by Z, and then we add the principal point Cx. And if I now go back one slide, this is exactly what we did with Y here. So imagine we are talking about X. Now it's Fx by X divided by Z plus Cx. This would be this row, and for Y it's like exactly what you've seen on the last slide. So this equation allows us converting 3D world points into 2D image coordinates in pixels. And it's really important that you fully understand this equation, because it will be the basic for the rest of the content we are discussing in this lecture. For this, I recommend you to go at this web address, where you can interactively play with each individual parameters and see what effect they have on the final image. One more note, if you read up the K matrix somewhere else, you might encounter one more parameter, namely this Q. It will be here, and it is force set or fixed to 1 in our model, because we are mainly talking about CCD digital sensors. What this Q parameter models is is when your pixels are do not have a right angle, but rather have some skew. This could happen with film cameras, where the film is deformable, but CCD sensors are rather sturdy, so it's safe to assume that skew is 0. And this is why we are ignoring it. Also, the OpenCV library does not allow you to calibrate the skew with the basic camera model. You might wonder, yeah, this is all nice, but does it model the real world? Does this actually work? And yes, we can already build the camera like this. It will look something like what you see here. We basically punched a hole in the camera cap, which is our pinhole. And there's also a small community which does photos like this, and they look something like what you see here. So if we take a look at the photo, we already recognize, okay, this is the real world. We see what was photographed, but we also see some bad things about using pinhole in real life. First of all, the image is rather blurry, and next, the image is also a little bit too dark. So what is the issue? It's the size of the pinhole. If you make it too large, then things start to become blurry because more than one ray of light hits the image at 1 pixel. But also if you make the hole too small, then not enough light hits the image sensor and the image becomes dark. So it's always a compromise between a too dark image and a too blurry image. And this is like one compromise which you see here. So can we maybe have both, like a big pinhole, and so we get lots of light, and but still keep the image sharp? Well, yes, we can, but we need to add something like this in front of our camera. This is like a cut of a real lens. And what this does on top of a pinhole, it collects the light, so there's still just a single ray of light hitting a pixel, while initially there are multiple rays of lights collected to a single one. However, the issue with this, it makes our camera model more complex and things in generally become more complex. And what does this complexity mean? Basically, this is what causes our lens distortions in the image, which we tried to get rid of in the first image of this slide deck. So let's add this thing mathematically to our camera model. And first of all, what are lens distortion in more detail? Here you see an image which seems heavily distorted, but actually this is an image with no optical distortions. What you see here are purely perspective distortions. This is like photography, or aesthetically this is maybe also not desirable, but if we want to do computer vision, this is what we actually want, because in this space everything is linear, the lines are straight, and we can compute things and distances. As you can see, this is blurry at the edges. This is because this is an undistorted image. The distorted counterpart to this image is this. And the distortion you see in this image is radial distortion, like heavy radial distortion, because this is captured with the fisheye lens. The fisheye lens has a special property where the angles between things are reproduced correctly. So the right angle here is still right, but the lengths are not correct, and also straights are not straight, which you can easily see also in the upper left corner of the image. So if we want to go from this image to this image, how do we model this mathematically? Well, the answer is this formula here, but before we start discussing this formula, let's take a look what it does. This is depicted in this image, a little bit simplified. So we see the effect of this radial distortion applied to a checkerboard pattern, and the checkerboard is distorted, and the yellow arrows here denote the distortion strength. So the end is the distortion coordinate, and the start of the arrow is where it should be if it's an undistorted image. So how do we model this? Well, we start with an undistorted point 2D point P and obtain a distorted point PD. And we do so by multiplying the point with this bracket. And why exactly this one? Well, actually, we require surprisingly little about on the function which we model here, because this bracket here is just a Taylor expansion of some arbitrary function of radius. So r is like the distance from center of any point in here. And then the parameters of radial distortion are k1, k2, and k3, and they are just the coefficients of Taylor expansion of this unknown function. Furthermore, we only kept the even coefficients of Taylor expansions, like square to the power of 4 and to the power of 6. This is a rather arbitrary choice, but it's quite common when modeling radial distortion. My guess is that you do not have to consider the sign of the radius if you just keep the even exponents. And the image on the bottom was generated synthetically by setting k1 to 0.1, and k2 and k3 were kept to 0. So this is if k is positive, and if it's negative, then you get the inverse direction of the errors, and it will resemble the fisheye distortion you've seen before. One thing to note here is that the function only depends on the radius. This means it's radially symmetric again around the origin, which is here. So while this radial distortion is probably the strongest distortion you see in images, typically one adds one more distortion, and we talk about it on this next slide. The next distortion is the tangential distortion. Again, you find the formula here, but we first talk about what it does intuitively. So what you see here is again the distortion of a checkerboard pattern, and yellow arrows indicate where things move. And if you look at the arrows, it resembles tilting the checkerboard pattern slightly back on the left side. And this is exactly the effect that this distortion tries to model, namely that the image plane and the lens is not properly aligned, that there's some angle between them. This typically happens if there's a bad build quality of the camera, then things are not really well aligned, and then you have this distortion. This distortion is modeled by the coefficients p1 and p2. X and y are the 2D pixel coordinates of the point P, and we also have the radius in here. So this time this is not a Taylor approximation, but analytical derived tilting of the image plane. So now that we have talked about the two major distortions in conjunction with lenses, how do we put them together? We do it like this. So here we have our undistorted point P, and we apply the radial distortion, and then we add the tangential distortion on top. And the combination of the radial and the tangential distortion, we give this a name, which is the function delta, like distortion. So delta of an undistorted point P is its distorted position. So now that we have modeled the lens, we need to attach it to the pinhole camera we described before. And we do it like this. This part is the same like before, but we apply now it describes the mapping from a world point to the camera space, and also includes the Z division, and only now we apply the lens distortion. And then we continue with the K matrix, which we defined previously. So again, keep in mind that both the K matrix and lens distortion are applied post-projection. So the Z coordinate is cancelled out, and we are only talking about 2D points here. So this is now the full camera model we will use for the remains of the lecture, and let's talk now about how the full intrinsic parameter vector C looks like. It looks like this, and it contains the focal length in X and Y, then the principal point in X and Y. So this is these four parameters are the K matrix, or encoded in the K matrix, and then we have the delta distortion, lens distortion function, which has the three K's from the radial distortion and the two P's from the tangential distortion. So these 9 parameters are like the typical intrinsic parameters which are used like everywhere. However, note this that there are only 2 kinds of distortion included, and there are also more distortions which one can consider. Like if the lens is tiltable itself, it's the tilt shift distortion. And if you talk about microscopes, then things also get more difficult, or at least different. So before continuing with how to actually measure these parameters, let's take a look how a real distortion field might look like. So what you see here is the distortion field. It's like lots of this yellow arrows, but drawn per pixel, and therefore we only look at their strength, which is encoded between blue, which is like 0 length, and red, which is maximal length. So this is normalized from 0 to 1. And the camera which we calibrated here is Logitech, this one, which is a typical and rather cheap webcam. And as you can see, we have the radial distortion, which is pretty prominent here. And it also has a slightly shifted principal point, because you see more of the radial distortion on this side than on this side. And if you look closely, you also see a little bit of tangential distortion in here. Like here, this spot is slightly brighter than this spot. So there's like also a small tilt of the sensor. And this is for a rather simple webcam, which comes quite close to the pinhole model, because things are simply that small. And it's also true like for cameras you have on a cheapish smartphone, like the more expensive one have multiple lenses with more complicated optics, but this is like a simple optic as you can get. And still we have radial and tangential distortion. Okay, but how to actually measure something like this? Of course, this probably tells you that you cannot use a ruler or something to measure these things. So what do? Basically, we need several point correspondences, like n in general, between 2 points and 2D points and 3D points. Here we must know the coordinates of the 3D points, and we try to find them in the 2D image. Because we know where they should be, we can derive the distortion parameter C. And deriving them means finding the optimal set, and optimal means here that we are minimizing this error. So what are we minimizing? Let's first take a look at the norm here. So we have small p points, which is like the observed 2D points, and then we have our camera model, or our camera projection function p, which projects our known 3D points given all the parameters it takes. And so what we are doing, we are trying different C's, intrinsic parameters, such that this norm is ideally 0. And we do not do this only for one point, but as said initially for n points. So this is the outer sum which goes until n here. But then we also have another sum which goes until m here. So what's this? Yeah, so basically we are not talking only about one image with multiple 2D points here, but multiple images with multiple 2D points here. And if we turn to the indices in the norm, this is what they are describing. So we have a 2D point, a particular one, so pi in the image J. And looking at the indices here, we also have the respective, or we find the respective 3D coordinates big pi here, but we see that the rotation and translation is per image. So what this means that we are observing the same n 3D points in m different images where we have a different rotation and translation per image. The thing why we describe it exactly like this, you will see a little bit later, where we are discussing the full calibration procedure. But keep in mind that we have multiple images and we have different, or allow at least a different rotation and translation per image. So how do we actually minimize this sum? We do as follows. First, we only consider the intrinsic parameters k. So we assuming the lens distortion to be 0. And because k is just a matrix, we can obtain a linear least squares solution, like using the direct linear transform. If you want to learn more about this DLT thing, I refer you to this book. And yeah, obtaining a least squares solution means we form linear equation system like this. So A is a matrix, and x are the parameters we want to solve for, and b are our observations. And this gives us an initial solution while not considering length parameters. Why? Because the length parameters are nonlinear and this would not work. So once we have this solution, we do nonlinear optimization, which means we are using Levenberg-Marquardt, and we are adding this delta function to the optimization objective. And for you to recall, the nonlinear optimization always needs a good initialization to converge. And this is what hopefully this gives us. And from this solution, we compute the gradient at that point. This means the partial derivative of the function p in respect to all of our intrinsic parameters. And when we have this gradient, we can again make a linear equation like this. It should resemble this one if you look at it. And this gives, this way we linearize our nonlinear function and take a step into the direction of the gradient. Like this minus means we are descending into direction of the minimal error. And we do this several times until we converge. Like we do not improve any further, or whether we have some other criterion which says we are done. So the remaining question is, where do we get the correspondences from between 3D points and 2D points? Yeah, so I noted it briefly previously. The 3D points come from a known geometry. So we take pictures of something where we exactly know the size of. And while it doesn't matter much what exactly we take here, we should still differ. So we might take a 3D object, which is called calibration target in this context. And the advantage is if we choose a correct one, then we only need one picture to perform a calibration, like to determine all the parameters and see which we talked previously about. The issue here is that then a 3D target is difficult to manufacture, at least if it should have high precision. And we want it to have high precision because if the 3D points are somewhere else due to bad manufacturing, then this translates directly into a bad calibration, because we do not account for this and then think that, yeah, this must be the lens, and not because the 3D target is like messed up. Therefore, the second choice for obtaining non-object geometry is a 2D target. And those are easy to manufacture because all you need is to print something. And yeah, 2D targets basically means you print something on paper and then you know, okay, it's flat, or you assume it's flat, and you're done. And printers are reasonably accurate in printing things. The issue here is then you cannot determine all of the parameters from a single image if you are only using a 2D target. This means you now need multiple images, and because you have multiple images, you have more variables which you want to determine. So let's take a look at how these targets might look like. On the left, you see a typical, or a 3D calibration target which people used to use. And as you see, it's composed of 3 planes which are not attached to each other, but not necessarily at the right angle. And the calibration points which you want to find in the image are these white blobs. And this is crafted especially to allow this by thresholding. So you turn this into black and white, and then you only have like black regions and white regions. And then you still need to figure out which of the white blobs corresponds to which one here. This is why you have different sizes of blobs here. And then you try to sort them into this rectangular structure. So you count 1, 2, 3 and so forth. So this is 0.1 and this is 0.100. And if you matched all of them, you know which points you're looking at. But as said, it's difficult to ensure that this angle is exactly of what you expect it to be. On the right side, you see a typical 2D calibration target, which is simply a checkerboard pattern. And you use these points for calibration. Why these points, we will talk briefly about. But the way to figuring out which 3D point this one corresponds to is the same like here. You are ordering them to a known grid. So this is what the colors symbolize here. This is like 0.0 and this is the last one, and they are ordered in rows and identified by the color. The drawback of detecting things like that is that the whole pattern always needs to be visible, because if a part of this is cut out, you cannot establish this order anymore, and then you do not know which corner corresponds to which 3D point, and you don't have point correspondences. And this is a limitation, because imagine if you move the pattern to the edges of or the corners of the image because you want to measure things here, and it happens easily that you do not see parts of it anymore. So you want to enable detecting this pattern even if it's obstructed by something. So like said previously, this is like you do not do this anymore because it's not precise, and people do this. And for enabling obstruction of the pattern, you can place little markers in here, which are like QR codes, which allow identification of this corner next to it. So yeah, just show you an image of it. This is what you see here. So we again have the checkerboard, and we have this markers, and this marker basically tells, okay, this is ID 20 over here, and this marker says, okay, it's ID 0 over here. And we have it obstructed by the mouse, and we still can detect the corners which are visible. Okay, so as said previously, why we are using exactly these corners, because I mean we have corners over here and over here, so why not also using those? For this, let's take at the following close-up. This is like one edge of the pattern before, and what you see in yellow here is the gradient strength of the 2D image. The gradient is here like the bilateral Sobel filter, and the brighter the yellow is, the stronger the gradient is. So what you see here is the image is blurred, so we cannot know exactly where the corner is because things are blurred. And so what you typically do is walk along the gradient until you find a maximum, and then use that as a point. And if you now look at the corners which are not at the crossing between two black tiles, then you see that the gradient maximum is on the outside. So if you use this one, then you overestimate the size of the quad, or the location of your 2D, of the corner location in 2D. And because we have this cross in here, the gradient is constrained to be at the maximum at the exact location where we want it to be. And this this overestimation also happens like as underestimation if you swap black and white. And this blurriness does not only happen if you have like a bad focus on your lens, but it might also happen due to insufficient resolution of the image. And so what this does is giving us, even if the image is sharp, sub-pixel accuracy. And this further improves the precision of the calibration. So this is why we use exactly this calibration pattern to obtain a high resolution of the 2D points. Okay, what you see here is like one 2D point, and because of the marker you know which one it is, so you have one correspondence between a 2D point and a 3D point. But how many of them do we need? And so this is the size of the marker, and how many images of the marker do we need. We discussed previously that one image is not enough if the calibration target is planar, but how many do we need? Do we need all these views of the board, or So what this symbolizes is that we are taking multiple pictures from different views, and we also ideally would like to know how to select the views where we capture the calibration pattern. But before we continue with determining all of this, let's talk about why using only one image of a planar calibration pattern is not enough. For this, let's turn back to the initial sketch of the pinhole camera, and let's assume that we have only a planar calibration pattern. So this is what this purple border is supposed to suggest, that this is not a 3D person, but rather a cardboard cutout of a person, which is then projected on the back-facing wall, and furthermore assume that this cardboard cutout is parallel to this back-facing wall. And yeah, so this is our geometry. We have the cardboard cutout at a distance of z to the pinhole, and then we have focal length of f, which is the distance between the pinhole and the image plane. So what is the issue here? Let's imagine that instead of capturing the image of this size on the back facing wall, we captured an image of this size. Now we are calibrating the camera. So this means we do not know the focal length here. Also, we do not want to take a ruler and measure the distance between the camera and the cardboard cutout because it's cumbersome. So we also do not know the distance z here, and we are trying to estimate both simultaneously. Now we captured a slightly smaller image on the image plane. What does it mean? Well, first of all, and more intuitively, it might mean that the cardboard cutout is slightly farther away and thus it appears smaller. So it's this. But because the focal length is unknown as well, it might be equally that the focal length is slightly shorter. And we cannot distinguish these two cases. However, note that this also visualizes the effect of the low focal length quite nicely, and a smaller focal length results in a smaller image, thus a larger field of view. Alternatively, if the focal length is larger, it means that we are zoomed in a little bit more. So this is the intuition for the focal length, which you can derive here. Yeah, but the problem which we are confronted here with is that we do not know whether the object is farther away or if the focal length is smaller. And this problem is called calibration singularity, or the pinhole singularity. Note that we could resolve it if we say that the cardboard cutout is not parallel to the image plane anymore, because if it's tilted somehow to the image plane, then we have a perspective shortening in here, and we can disambiguate the distance z, and in turn this allows us to precisely derive the focal length f. So the first pinhole singularity is like the one we just seen. It is only occurs if the calibration plane is parallel to the sensor, so the angle between them is 0. And in this case, we cannot determine the focal length. However, if we turn to the other extreme, namely if the angle between the calibration plane and the sensor is 90 degrees, then we cannot determine the aspect ratio. That means the pixel aspect ratio here, like the ratio between fx and fy. Well, intuitively, this wouldn't work anyway, because if you're looking at the plane at the angle of 90 degrees, it's just a line and you don't see anything. But this issue also occurs if you come close to 90 degrees, like if you are above 80 degrees or about 70 degrees, then you cannot determine the aspect ratio properly anymore. The same is true here. If it's not exactly 0 degrees, but close to 0, then you also cannot determine the focal length. And then noise is like weighted too much in these cases. And finally, there's one more important degenerate case, and it is when all planes or plane views are coplanar. What this means, you can image if you place a camera which looks at the table, and then you move the calibration pattern on the table. Then all calibration views are coplanar with the table plane, and then you do not gain any more information, because it basically is the same as if you would be looking at the single calibration pattern, which would be larger. So these three singularities are like the most important ones you should consider while calibration. And there are some more which are described in this paper cited down below. So the next question is, given I observed all this avoiding the singularities, did I arrive at the good calibration? So how do we measure whether calibration is any good? The first thing which might come to your mind is using the reprojection error, which is like the sum we try to minimize when calibrating. The issue here, or with this approach, is that you are looking at the residual error with the reprojection error. What a residual error is, please refer to the book cited below again. But the basic intuition is that we are only measuring the distance between our noisy data and our estimated model. And this is not the error we're actually interested in, because we want to know whether this is generally a good model and not only in respect to the data we captured so far. Particularly, we can always get this error to zero if we run low on data. So this model, or we have like 9 intrinsic coefficients. So say we have 9 degrees of freedom, and if we only capture 9 constraints, that would be like 4.5 2D points, then we always can make this error zero. So yeah, this is like the issue with residual error, and it is always biased towards the data we captured so far. So is there any way around this? And yeah, actually there is. And the proper way is to estimate the uncertainty, like the covariance of our intrinsic parameter C. It means, yeah, so this is, let's say this is 1, but is it plus minus 10, or is it plus minus 100? So this is covariance. And if we can estimate this, we know how precise our parameters actually is. So how do we estimate this covariance? The method is the backward covariance transport. And the approach is basically you use the local linearization, like the Jacobian, which we derived earlier when talking about nonlinear optimization. And then you assume some covariance on your input data. Here you can simply put in the identity, and it as a rough approximate of the variance of the pixel data, and in this case it means you only capture the 2D image position up to 1 pixel. Yeah, which is a sane approximation to make, and given this assumption, you can then compute the covariance of your parameters. Yeah, as a note, this plus here means pseudo inverse, because this is not a square matrix, and therefore you cannot take a normal inverse for it. So now that we know the variance of the parameters, we can monitor it to see what is a good pose and what is a bad pose, or what is a good view of a pattern and what is a bad view of a pattern, what improves my covariance and what does not give me any more advantage. And this is what we did in the following experiment. What you see here is the variance of the individual parameters. Like on the left side, these are the focal length and principal point, like the intrinsic parameters K, and these are the lens distortion parameters K1, K2, K3. Yeah, the parameters of the distortion function delta. And on the x-axis, you see a series of images being captured. And as you see, the variance slowly declines here, but at frame 10 something happened, and then the variance dropped significantly for the focal length. And on the right side, with the distortion parameters or radial coefficients, no such thing happened. So what changed at this point? Here we did a specific, or we captured a specific movement between frames 2 to 10 and then from frame 10 on. And the specific movement looked like this. What was happening in the gray area here is that we did a parallel shift of the board. So the calibration pattern was parallel to the image plane, and we were just moving it up and down and left and right in the image. And as discussed before, this is a bad situation to estimate the focal length, and therefore the covariance stayed high. At frame 11, we started tilting the board around its central axis, and also as discussed before, for the focal length, this is what we need to do, and we also can observe this in the covariance, which drops significantly. However, on the right side, as discussed previously, there's no such jump. So it seems like the radial coefficients are not at all sensitive to the shift and tilt. To verify that, we did a complementary motion of this. This means we first did the central tilt and then the parallel shift. This is what you see on the bottom now. And as expected, for the focal length, the variance drops immediately and stays low or does not improve significantly afterwards. However, if we turn to the radial coefficients, we see that as long as we were only doing central tilt of the board, the variance stayed high. So this means that tilting the board in the middle of the image somehow hinders estimating the radial distortion properly. And only once we hold the board parallel to the image plane and start shifting it, the variance drops significantly. So what does it tell us? It says that the two parameters show complementary behavior to each other. So while for the intrinsic parameters, we need the tilt to drop it significantly, or like here. For the radial distortion coefficients, we need the shift, which again is bad for the intrinsic parameters. Yeah, so the bottom line maybe is that you need both the shift and tilt. But how to derive a calibration strategy from this? Yeah, let's look at the following. So here we have the variance of the individual parameters, and the strategy would be, if it's intrinsic parameter like focal length or the principal point in this case, we want to maximize the angular spread of the views captured around the board. So if, let's say, we capture this 5 views, we then continue capturing these views additionally to maximize the spread. And this hopefully helps estimating the intrinsic parameters. While if assume one of the distortion coefficients was most unsure, we would do this. We would be placing the board into the corner regions of the image. The intuition for this is recall the radial distortion is radially symmetric, so if we move it to one corner, it helps us everywhere. And also we want to measure how it behaves in its maximal region. So if here we have the maximal distortion, we want to know exactly how it looks like. And yeah, this is then our optimal pose selection strategy. And if you want to learn more about it, I refer you again to the paper cited below. Let's look now at an example of applying this strategy. So first we start with 2 fixed poses of the pattern. one where the pattern is tilted and one where it's parallel. The intuition behind this is that we now have a rough estimate for both the focal length or the intrinsic parameters in general and the lens distortion parameters. And then our pose selection strategy kicks in, and in this frame obviously the distortion was most uncertain, so we placed it in one of the corner. Then it still was not enough, so we placed it in another corner, and now we start maximizing the spread by tilting the board and so on. What you can take away from this is that these 9 images show a complete calibration until the values did not improve any longer, so until convergence. So this means if you take care which frames you capture, you can get away with only 9 calibration frames and obtain a precise calibration. However, nowadays you do not any longer have to do it manually and think about all of this. The method which I just described is now available online at this web page, which provides you a guidance through the calibration process. So it shows you the 2 initial frames which you seen here, and then it starts interactively guiding you through the calibration process until convergence is detected. Furthermore, this also aggregates existing calibrations. This means that if somebody with the same camera like you already visited this site and completed the calibration, then you get the option to just download a calibration which fits your camera instead of having to calibrate it again. Conversely, if you if you calibrate your camera on the web page, it will remember the calibration, and you can come back to download it, and it will be also provided for other people to save them calibration time. And with this I want to conclude this lecture on camera calibration, and thanks for watching.